What really makes DuckDB stands out is the fact that this is an in-process engine.
It is a powerful tool for auditing and debugging that requires zero complex infrastructure, turning local market files into a fully traceable data lakehouse.
So now let's talk about the reality check. So what's the catch here? Hi everyone, my name is Grzegorz Rybak. I'm a senior data engineer here at DeepSense AI, and today with me is
Cezary Gorczyński, and I'm a data engineer as well.
Today, we'd like to talk to you about DuckDB and DuckLake technologies, which we casually drop as a lightweight data platform revolution term. Very catchy, I know. And we'd like to invite you to our talk where we dive deeper into whether this technology combo solves all of our problems as an AI and data consulting company. Let's start from the premise. So what is a typical client problem that we're facing in this space? It's actually two kinds of problem. The first problem is this kind of a greenfield project and its dilemma. So the premise here is that the client comes to us expecting an ML-driven or otherwise generally analytical solution. And we're immediately faced with two choices. Either go quick, fast, agile, with a small solution that we're going to build into a bigger one, or we're going to start with some heavy platform. So with the small solution, we would start with something like pandas, maybe polars even, pipelines that would work on some data lake. However, we quite quickly get into a situation where, especially with pandas-based workflows, where those approaches become quite inadequate when our data or our project grows in scale or complexity. Specifically, the reproducibility of those solutions generally degrades over time, as we found it. Especially, we're going to talk about that in the DuckLake part, how this solves this problem, but also generally interoperability as well, and how those ETLs inside our solution, generally speaking, aren't so again shareable, let's say, with other wider data teams. And generally speaking, we find the need for a warehouse solution quite early as well. And we can, without diving too much into like heavy platforms, we can get into a solution such as Redshift or Google BigQuery, but these arguably already introduce some vendor lock-in, as well as people that work with those solutions might already know they introduce some sort of their problems as well. And there is a reason why solutions such as Databricks or Snowflake exist and gain such a popularity. And speaking of those, we could also start already with those. So we could start with those heavy platforms. But then the immediate problem is the fact that whilst we know that in terms of the scalability, that solution will hold, the problem is with generally this feeling of an overkill. What's the good use of this huge distributed PySpark cluster on our Databricks if we're, especially at the beginning, start with just gigabytes of data at the client's problem, and this introduces also, most importantly, a big vendor lock-in. So those factors generally make it quite hard for us to really have this conversation with the client about going with that solution, with this solution already. And generally speaking, we find this feeling where everyone needs big data. No one wants to commit before necessary. And we put big in single quotes here because we're going to talk about that as well further on. But yes, that's the first problem here. Then there is a second problem, the brownfield project. So this is a situation where the client already has an existing infrastructure and very often is highly inadequate, but cannot be replaced. And the challenge here is that we still need to build modern analytical work that basically omits those boundaries and this legacy lock-in. And the goal here is still build a robust data solution, but keep a great pace in delivering value most importantly, not just engineering solution. And very importantly, don't get stuck at organizational conversations, whether that is changing the vendor or bypassing the current system, if changing vendor tools even is possible. So that's the problem. And in terms of our historical attempts, like many of us in the industry, we started off this 10 plus years ago with a data lake solution in such case. But we face the typical problems with that regards, which is over the time, the DevOps necessary to build this solution is growing. And generally speaking, you're faced with very often with many, sometimes quite brittle ETLs. And usually there's this situation where there is a single data team that really touches those pipelines. And again, that interoperability mentioned in the first problem really comes in here and is a bottleneck in high performing data teams. Then we look into Lakehouse solutions, and this is a very promising concept. After all, this talk is also talking about such a technology combo. But we found issues when implementing specifically Iceberg in this context on our existing data lakes clients, basically. And that is because we found issues with implementing the Iceberg's catalog. We found the issue with having the actual compute engine still needing to be distributed in order for this Lakehouse to actually operate correctly. So effectively, we have a heavy compute, high maintenance, distributed problem here. So after all, if we already have this problem, then we looked into a third solution, which is a cloud data platform. And this is the one that we mentioned actually already in the problem number one, right? So it means big vendor lock-in, and it means, generally speaking, this kind of all or nothing approach. So that's the premise. Now let's talk about the solution. So first of all, let's start about DuckDB. So DuckDB, in general, is your typical modern analytical engine. And that means this is a columnar SQL engine that runs the queries in vectorized manner and leveraging multiple cores during the query execution. And importantly for DuckDB, also implements this predicate and projection pushdown. So that means for data sources that allow this natively, such as, for instance, Parquet. That effectively allows you to and allows the engine to really only transfer the data, only process the data that the query really touches, and not just reading the data row by row, or generally speaking, reading unnecessary parts of the data. But that isn't unique. Snowflake, BigQuery, Redshift, those warehouses, those solutions already implement most, if not all, of those similar concepts. What really makes DuckDB stands out is the fact that this is an in-process engine. So you can picture on the left-hand side this kind of typical online analytical processing engine where you have like big warehouse. It's always on. It behind the hood, there's quite some involved orchestration around it as well. Whereas in DuckDB, if you think about DuckDB, this is an in-process engine. So you can think of this as your OLAP engine that basically just boots up the moment you start your process, performs the logic, and then shuts down, for instance, right? It's a single binary that fits on one machine. So that's basically the critical distinction. DuckDB combines this modern columnar analytical engine with this in-process model, allowing you to have a warehouse performance, but without a warehouse infrastructure setup. But you might think, okay, Greg, I've heard of an in-process SQL engine before. It's called SQLite. And I mean, there is a reason why there's still all those solutions existing. And I mean, SQLite was way before, Databricks or Snowflake was popular, right? And yes, you'd be right. DuckDB does share fundamentals with SQLite. So that means it is also an in-process database, meaning no typical kind of client-server database structure like it is with Postgres or other popular DBMSs. It's easy to embed in applications because, again, it's in process, right? So you can run it as well in your long-running cloud data pipeline, as well as basically directly in your in-app logic, right? Or also, it's a database file-based kind of database, really, which means that you basically operate on file. You can have your .SQLite, or here you can have your DuckDB file. Though with DuckDB, actually, there's a caveat. You can even read the for instance, Parquet files directly kind of virtually, so you don't necessarily need that database file, but generally speaking, this is the same concept, right? But the difference is with the details with regards to how the data is read. SQLite reads this in row-oriented manner, so it's focused on those fast inserts, on those key lookups, so basically small data changes, but very frequent. Whereas DuckDB, again, runs in a columnar fashion, meaning this is optimized for loops, scans, for joins, for aggregations, and that's the main difference. Whilst they have the same deployment model, so they're both embedded SQL engines, SQLite is for transactions and DuckDB is for analytics, meaning we can finally have this analytical engine player in this field of in-process engines as well. And that locality of DuckDB is really the key benefit here, which is we talked about this big data in quotes, right? And that's important. Historically, we had this notion of big data that needs to run on your Hadoop or any other base or your PySpark cluster even, and people were associating this to big data. But nowadays, what was big can be actually small to medium scale. It can nowadays potentially just run on your single node. And those cases really cover 80% of the real world use cases from our perspective of a consulting client company. And so this is the mental shift. If it runs on your laptop, it means it's highly portable and you can still deploy this as a simple, cheap production setup. And DuckDB further intensifies this feeling by allowing a zero ingest workflow, which means that earlier on, you needed to have a customized ETL for each of your data sources to move the data to your, whatever that is, your data warehouse, for instance, right? Before this analysis could even begin. But now, with the DuckDB, you can effectively just attach to your multiple other data sources or data engines and just read from it basically natively directly. So that allows you to have this BI logic kind of as if directly on the data. And it also allows this new capability where, for instance, again, thanks to the fact that this is an in-process database, it allows you to just plug in directly to your data from, for instance, a dashboard if you need to, right? So that's the benefits of the DuckDB. But that's just one part. Now I'm going to hand over the mic to Cezary about the second part.
Okay, so my turn. So building on the power of DuckDB that we just explored, let's now transition to the DuckLake, which serves as the essential extension to unlock enterprise-grade data platform features directly on top of that analytical core. So DuckLake is a high-performance lakehouse storage format designed to bring database-like management to your Parquet files in the cloud. It extends DuckDB's capabilities by adding AC transactions, schema evolution, and time travel to your storage. It acts as a management layer that allows DuckDB to query massive cloud datasets with the stability of the traditional data warehouse. DuckLake acts as a powerful extension for DuckDB, bringing enterprise-grade data lakehouse capabilities to a single node architecture. It brings the gap between local analytical efficiency and robust data platform features, like version tables and time travel, schema evolution, lakehouse discipline in a single node architecture, and access control. Let's consider the following architecture, which we call the Holy Trinity of data. This design philosophy separates the brain, the heart, and the body to create a system that is both incredibly fast and easy to maintain. At the center of this stack is the heart, powered by DuckDB. As a vectorized analytical engine, DuckDB processes millions of rows per second directly on the CPU. It serves as the high-performance engine that drives all our computation without the need for a massive distributed cluster. Supporting this is the body, our storage layer built on zero ingest Parquet. By using Parquet, the open industry standard for highly compressed, immutable columnar data, we eliminate traditional load step. DuckDB queries these files directly where they live, providing a zero ingest workflow that serves both time and storage costs. Finally, we have the brain, which acts as our central source of truth. While many starts with SQLite, we have evolved this component to Postgres to handle more complex metadata, schemas, and snapshots. The brain guarantees transactionality and ensures that the entire system remains synchronized and reliable even as your data operations scale. The intelligence of this system is the metadata brain, which orchestrates data through a ACID process. It begins with the write phase, where new data is saved into immutable Parquet files by never overwriting existing data. The system ensures total integrity and enables snapshot isolation. The critical step is the metadata commit. The brain, Postgres or SQLite, records a new snapshot ID, capturing the exact state of the table at the moment. Because this happens within a transactional database, the update is atomic. It is either fully committed or doesn't exist at all. Finally, during the merge on read phase, DuckDB consults the brain to identify active files, pulling the latest versions while ignoring locally deleted data. The value we unlock. First, we achieve absolute portability with zero vendor lock-in, as your entire data lake lives in local files that are as mobile as your code. Second, we provide reliable time travel, allowing you to query the database exactly as it exists at any point in the past for effortless auditing and debugging. Third, our seamless schema evolutions allow you to add, modify, or remove columns without downtime, migration, or breaking existing queries. This setup maintains Lakehouse discipline by bringing transactional guarantees and schema evolution to lean architecture with the simplicity of a local tool. Let's dive deeper into the time travel and schema evolution. Time travel is just as straightforward as a metadata brain maintains a perfect history of every snapshot taken over time by simply adding the timestamp or version codes to your standard SQL. You can instantly query the database state from the past for effortless auditing and debugging. This allows us to have schema evolution, which is enhanced by version locked schemas, ensuring that queries into a past past do not see future columns or structural changes. It is a powerful tool for auditing and debugging that requires zero complex infrastructure, turning local Parquet files into a fully traceable data lakehouse. So let's back to Greg. Your turn.
Thank you, Cezary. So now let's talk about the reality check. So what's the catch here, right? And as always, there's always some catch. There's no free lunch. And with this architectural decision of DuckDB and DuckLake come also architectural trade-offs as well. And the main one really comes from its main benefit as well, which is the fact that this is all in process. This also means, because it's in process, it locks you to single writer constraint. Meaning, whilst you can have multiple read queries, whenever your processes write and need to write concurrently, that is going to be a problem. And in our solution, our proposed solution, as Cezary showed, we are using SQLite backend for the DuckLake, and that allows us to have a serialized multi-writer setup. But if you want to have full concurrency, DuckDB or actually DuckLake does allow you to change the backend to, as mentioned earlier, Postgres. But there is also a trade-off, because once you introduce a client-server database for this brain part of the Holy Trinity, we introduce a slightly less portability. So this is a trade-off. It is possible, but it's, as always, it's a trade-off. Then the second argument comes again from that same architectural decision, which is because, again, it runs in process, it runs on single node. That means you can only really scale that one execution node vertically. So you can't horizontally scale with multiple nodes. And actually, that single node, coming back to this not big data, scales well to terabyte scale. But if you need distributed petabyte fast scale workloads, well, then this isn't a solution for you. You should be looking into those specialized big data warehouses. And then we also have no true streaming capabilities. Whilst DuckDB, thanks to this zero ingest workflow, does allow you to have batches and even micro batches, and we would argue that this is actually more than enough in a lot of analytical use cases. That's why we put an asterisk to this point. However, bear in mind, if you need a real-time streaming capability, this is not a real-time streaming engine. Finally, the last part comes from it being a Lakehouse solution, meaning it can be prone to multiple or multi-small files fragmentation issue. And I'm actually going to dive into that. Luckily, DuckLake with DuckDB allow you to have those tools that basically allow you to have a compaction of those multiple files. Effectively, if you run into a situation when you have multiple small files, it might hinder your performance, and definitely you will see this also in the storage. But again, you can combat that. You can merge those fragmentized files or small files into bigger ones to prevent this input-output performance issues. And also, you can implement your data retention policy in terms of managing your snapshots so that they don't grow to too much scale over time. So the real trade-off here is that if you want to have warehouse performance and you still want to reduce the cloud costs as much as possible, you might need some maintenance in exchange, but this is a fair upfront trade-off. Now back to you, Cezary.
So in summary, while the massive enterprise ship is often stuck in the dry dock of complex planning and migration, our agile DuckDB and DuckLake stack allows you to start selling immediately and deliver real business value today. This sailboat approach provides immediate results with minimal decision and quick deployment, reaching critical milestones while the large project is still years away from launch. The true moral is that you don't have to wait for the centralized platform to be ready to gain enterprise-grade capabilities like time travel, portability, and zero-copy integration. Once the big ship is finally built, this entire architecture is fully portable, allowing you to seamlessly move your major ready-to-go data assets onto the larger platform whenever you choose. So to conclude, now you can choose this new approach, improve agility with both data lake and warehouse advantages and portable tech stack, and only move to major cloud warehouses when massive scale dictates it, ensuring your data strategy remains both fast and future-proof. So Greg, it's all from my side. Your turn. Or no? Sorry. I completely forgot that is something what we would like to remain and keep in our horizon. Can we go to the next slide? Okay, so we are really excited to build a micro intelligence platform that delivers warehouse-grade capabilities without the overhead of massive analytical environments. By embedding democratized metadata into local-first system, we create lean architectures immediately ready for advanced AI and RAG leverages. This approach allows us by bypass corporate interior and deliver business value today using an agile sailboat strategy. It empowers engineers to own their stack locally while managing a clear path to scale only when massive scale truly dictates it. That's all from my side. Thank you.
All right. Thank you, Cezary. And with that, that's a wrap for today. We're really curious, what are your thoughts on this technology combo? And if you found this useful, feel free to like the video and subscribe for more. Thank you.